In this video, we're going to discuss AVLTrees. Okay, so one of the problems with binary trees, as we saw in the last chapter or last video, is they can get out of balance. You can end up with a degenerate tree, so that destroys your search time. The way a tree is most efficient is when it's balanced. Okay, so what we want to do is find some way to balance the tree without having to reconstruct the tree every single time we add a node. So here's our basics. We want a balanced condition that must be easy to maintain, and we want a simple approach to force the left and right trees to have the same height. Okay? So to keep them as shallow as possible, we can insist that the left and right subtrees must have the same height by getting an empty subtree as -1. This is a standard approach, but then only perfectly balanced trees of 2 to the k minus 1 nodes would satisfy this criteria. K equals -1, just a root, k equals 1, k equals 2. But that's not reality. An AVL tree is identical to a binary search tree, except that for every node in the tree, the height of the left and right subtree can differ by at most 1. Okay, so this one is an AVL tree because the left and right subtree differ in height by 1. Here, though, they differ by 2, so it's not AVL. So, using a node like we did in the binary search tree, we augment it with height information. So, in this case, the addition of 6 would break the balance condition, and we need to correct it. The correction is made by a modification of the tree known as a rotation. And we're going to give you a brief introduction, but then I'll drive into deeper detail. So we've got 4 cases. An insertion into the left subtree of the left child of alpha, an insertion into the right subtree of the left side of alpha, an insertion into the left subtree of the right subtree, and an insertion into the right subtree of the right child. Now, 1 and 4 and 2 and 3 are mirror images. 1 and 4 occur when insertions occur on the outside, and those cause what's called a single rotation, and 2 and 3 cause a double rotation. So here's a first way to look at it. Case 1, an insertion into the left subtree of the left child of alpha. Okay, we insert we basically need to then rotate. We'll take K1's child and make it a child of K2 and make K1 the root. Okay? Right subtree, insertion of the right tree of the right will do the same thing but the other direction. Insert to the left, we're going to have to muck things around because now it's an inner node. And similarly with the right. So here, the height differs by 1, we don't need to transform it. Height differs by 2, we have to. K2 violates the AVL balance property because the left tree is 2 levels deeper than its right subtree. This means we are in case 1. Similarly, what we have to do is we need to rebalance a thing. Now, one thing we have to keep in mind, this doesn't work if the tree isn't AVL to begin with. If it's already out of sorts, then you can't really count on it. Okay? So, if we've given this, we can guarantee that these rotations will preserve the ordering. Okay? I'm going to do some demoing using that tool, and then we'll come back and talk a little bit more about the rotating, because that is the tricky part. And then we'll look at some code. So here we go. We're going to, let's see, we're going to insert 1. Okay, left and right trees are the same. 2, we're still good. This time when we insert 3, we're going to throw the left and right sides out of balance. So what it's going to do is it's going to pick the node and it's going to rotate. Okay, so let us skip back because we have some more room between nodes. Let's say we're going to introduce 100. Okay, and then here we'll introduce 800, still good. introduce 100, still good. And then we'll introduce 250, still good. And we will then introduce 275. Now what this is going to do is it's going to throw things out of balance. But since it's an internal node, well, it's an external node, we're still okay. Let's see, so let's put in 290. And because of that, we had to do a double rotation. Okay? So, given that, let's go back and talk a little bit more about rotations. So, like we said before, there are 4 types of rotations. Left rotation, which basically takes a tree and rotates it to the left. In this case, I'll make Y the parent and flip everything over to the left. So let's take a look at it. Okay, so we have these aren't real parts of the tree, but they're pointers to help us keep track of where we are. So we've got our initial tree, right? If y.left doesn't equal null, then we're going to say x.right equals y.left, right? And we're going to break apart the tree here. The next step is if the parent of x equals null, then the right's just going to equal y. Else, if p.left equals x, which it doesn't, we're going to leave it alone, else p.right equals y. Okay? And there we go. P.right, parent.right equals y. Then we're going to say y.left equals x. And now we've rotated our tree. Similarly, with the right rotation, we're going to do almost the exact same thing, but we're going to flip all the variables. Now, left-right rotations, we just call left-right on x to y, and then we call on y to z. And you say, why don't we call it on the same one? Because otherwise, it won't work. It'll unrotate it. You have to call it on its parent. And similarly with the right-left rotation. So that's that part. Now we're going to do the interesting part, and we'll take a look at the code. Window here. Here we go. So, here we will first look at our node. I'm doing this a little bit differently than we discussed in the examples because there's some efficiencies you can gain there. So first off, let's look here. I define my node. It's having a balance factor, a left, right, but I've also added a parent. By adding a parent, you're going to simplify some of the implementation. So let's look at our actual implementation. So we're going to initialize our node. Big deal. Okay, we've got some pre-order, in-order, post-order traversals. We've got our search, which just like a binary tree, search tree does the same thing. We go left, we go right. The AVL stuff doesn't even interfere. Now, we're going to come back to delete because it's very complicated and unpleasant. Okay, we also have an update balance, which is going to have to update the balance factor. We'll see where that's used. We rebalance the tree is just our method to drive when we rebalance the tree. So, if we come to our insert routine. Insert. Okay, so part 1, ordinary BST insert like we've always done. Okay, you've done this as a homework assignment. Pretty straightforward. At the end of the insert, though, we now are going to say, do we need to update our balance? Do we need to rebalance the tree? So what we're going to do is come in. If the balance factor is less than 1, or less than -1, or greater than 1, if we're out of balance, we're going to rebalance. Okay? Just straightforward as that. Or set on a node. If node parent doesn't equal null, then what we're going to do is if node equals node parent left, then we're going to change the parent's balance factor. Similarly the other direction. And if the balance factor doesn't equal 0, we're going to rebalance. So now, how do we rebalance the tree? Here we go. If the balance is greater than 0, and node right has a balance factor less than 0, we're going to rotate right and left rotate. That's an int because we know it's an inner node. But notice we don't rotate on the node, we rotate on the node's right side, and then we rotate the node. Because if we don't do it this way, it won't work. Otherwise, if it's not an interior node, we're going to just left rotate. Similarly, we'll do the flip on the other side. Okay, so now the only thing we really need to get an idea about is how we actually implement the rotations. All right, so here we've got left rotate, where we basically just do similar to the algorithm we showed, except for one thing here, is here we actually have, well, actually the algorithm I showed had it. Here we actually have the parent. So we grab our y, which we're going to generate from that because we know it's the right side. If x right equal, we assign the right of x to x's left, so we move that subtree. If left is null pointer, we're going to, doesn't equal null pointer, we're going to set y's left's parent equal to x, like we had talked about. We're going to remap the parents, and then if the parent is null, we're going to reset the root. Otherwise, we will reset the left child of the parent. And then what we have to do after doing all this is we need to update the balance factor. That is the fun part. But when all this is done, we have our program, which I built a kind of hinky little tree into. There we go. We've got our left, we've got our right, and I actually had it printed each time. So here's our root, which we insert the 0. Okay. 1, we've got a root of 0 and a right side of 1. I should have put the root there. Anyway, here past 2, we've got the root equals 1 because we've rebalanced, and then 0 and 2 on the left, and so forth. So that's the basics of AVLTrees. It's complex, but I would highly advise playing with the code, seeing if you can write the rebalancing yourself. I will provide this code as a sample for you guys to look at.